So Saddlepoint Monte Carlo, which is cool because it's a bit different from what people tend to do when they do Bayesian inference or for this kind of problem, any kind of EM algorithm, whatever. It works very differently. This is joint work with Theo, who was doing an internship last year. He's now at Harvard University, and perhaps soon back in Europe, given the current situation in the US, but I should not, it's not funny. Robin, who is a neighbor, and he used to be at Dauphine, and Guillaume, who used to work on this project a long time ago, is now at INSEE. Right, so French election, what you need to know, even you don't care too much about it. I'm going to be interested in elections that have two rounds, right? Round 1, round 2. Typically in the first round, you have many candidates, like 15 maybe. And the second round, you might have 2 candidates, or 3 or 4 in certain situations. This is, for instance, if you look at the presidential election in 2022, there were 12 candidates in the first round. In presidential election, you take the top 2, and they go to the second round. So that was Macron and Le Pen. And Macron did 59 and Le Pen 31. You can abstain. So it's to abstain is like an extra candidate if you want from a statistical point of view. And the question is to analyze vote transfer. I mean, given that you voted for candidate purple at round 1, are you going to vote for candidate pink at round 2? I should not have picked colors because colors are also political. But anyway, all right. So this is something that occurs in France, but I'm sure you're aware that it's also the case in many other countries. Even in the US, there are some elections that work with 2 rounds. Right. So the kind of data we get, so that's very nice, and that's what started the project a long time ago, actually. In France, we have access to a lot of open data provided by the government, the public authorities. For instance, the Ministry of the Interior, they give you access to all the results in all the polling stations in France, right? So we have like 60,000 polling stations. A polling station is like 1,000 voters. Of course, some of them are bigger, some of them are smaller. And what you observe is this. First round, like 17 people voted for Macron and for Le Pen. So all the candidates of the first round. And second round, you have the number of people who voted for the 2 remaining candidates, or this third extra candidate, which is abstention. The fact you abstain. I'm not sure it's, so that must be the French word. I'm not sure in English you say abstention like this. You know? So mathematically, the thing you have to keep in mind is this matrix, right? The question marks here, that will be the number of people who voted like for Mélenchon at the first round and Macron at the second round, right? But you don't observe this. What you actually observe is the sum of the rows and the sum of the columns, right? You observe the total number of voted Macron at round 1 or Macron at second round, for instance, okay? So mathematically speaking, you have like, what's the name? Missing observation problem, where the actual complete observation will be this kind of matrix. There will be one such matrix for each polling station, but your actual data is just the row sums and the column sums, right? At this stage, if I stop, I'm sure that a lot of you will think, oh, this guy is going to do some kind of EM algorithm or Gibbs sampling, right? Because I said missing data, and you expect some kind of algorithm where you try to input the data given the observation, the missing data given the observation, and then infer the parameters. We're going to do something different, and that's what you might find cool about this talk. Right. So the kind of model you want to study would be something like this. So my matrix X, if I flatten it, it becomes a vector. I'm going to assume it follow a multinomial distribution with probabilities P, I, J, K. So K is the polling station. I is the candidate of the first round, J is the candidate of the second round. And you can simplify the model further by assuming that these probabilities are constant across polling station. Or, and I think the second model is already much more interesting, you can assume that the different polling stations have different marginal probabilities for the first round, but it is the transition probabilities that are constant. And typically, that's the best probabilities you want to estimate. Or you can go, you can be more ambitious and try to model these probabilities through a logit function as a function of covariance. And then you could study something like the transfer of candidate A to candidate B, to which extent depend on the unemployment rate, for instance, or stuff like that. Okay. So, of course, if you will observe the X matrices, the problem would be trivial. Okay, it's just a multinomial distribution. I mean, there are different models, but it would be quite easy to infer the parameters. Of course, the problem is that you don't observe the X's, you observe the row sums and row columns. I'm not sure that is something you're familiar with. I was not before I started this project, but if you were, I'd be interested to hear what you have heard about this. But apparently, it's well known in sociology and some branches of sociology, and they call it the ecological inference problem. And sociologists in the US, for instance, they are interested in trying to understand what's the probability you vote Democrat given you're black. And that's like 2 rounds of an election. First round is whether you're black or white or different categories of the population. And second round is the actual vote. Okay, so it's mathematically, it's the same structure. Of course, sociologically, it's a different problem, but mathematically, it has the same structure. For some reason, this was called ecological inference. And if you look into the literature, it has been studied for a long time, and people came up with different, more or less approximate schemes, which are not so satisfactory and which would be hard to apply to our current problem, because we want to deal with all the polling stations in France. So it's not a very big data, but it's already too big for current methods. All right, so keeping up with this mathematical description of the problem, well, I'm going to say that, again, X was initially a matrix, but I'm going to flatten it. So it's just a vector of dimension dx, with X listing, sorry. And what you actually observe is yk, which is axk, where A is a certain matrix, which corresponds to this operation of computing the sums of the rows and the columns, right? So keep in mind, the dimension of y is typically much smaller than the dimension of x. And A is not here on the screen, but if you will take 2 minutes, you will be easy to come up with a matrix A that computes the sum of the rows and columns. It will be made of ones that are strategically located. It's easy to come up. So from a statistical point of view, if I have one polling station, I need to compute this probability, because this probability would be the likelihood. Okay, you have some model on X, A is some fixed matrix, you actually observe Y, and that's the likelihood, right? Of course, in practice, we're going to have many polling stations, so the likelihood will be a product of such probabilities, but how do you compute this probability? That's the problem we have to solve, right? So I'm going to talk mostly about this nice application to French election, but ecological inference arise in many other areas. I could mention in particular privacy. There are a lot of talk about privacy. Well, a very easy way to achieve privacy when you have public data is to aggregate. But if you have aggregates, then it becomes challenging to do inference at the individual level, unless you use our approach, which might be a way to solve this. And maybe we are also close to inverse problems which have a similar structure, etc., etc. Right. So, as I told you, you might expect at this stage, given this kind of model I'm discussing, that I'm going to introduce a Gibbs sampler because as Benjamin pointed out, I'm mostly a Bayesian. I work mostly on MCMC and related algorithms. So you will have something like a Gibbs sampler where you will sample theta given x, x given y and theta. Okay. Again, x is like a latent variable. If you will observe x theta given x would be easy. Again, I'm assuming a simple multivariate multinomial model, so that should be easy to come up with this. But the second point, sampling for each polling station, fitting this matrix given the constraint, is a super hard problem actually. So in case you are a bit familiar with MCMC, at the beginning of history, there are people like Percy Diaconis who try to come up with clever ideas on how to mix properly in this kind of discrete space. It's super hard. I mean, we try to do something like that, and we are not going to do that. We are not going to use all this approximation scheme that people have tried to come up with in ecological inference. We're going to do something different.
Nicolas?
Yes?
So, sorry to interrupt. So on this naive solution, you still need to design a Gibbs sampler per polling station, is that right? Or do you design one for the entire set of polling stations?
Yeah, so, sorry, maybe it's a bit unclear on the slide. This will be like if you have one polling station. If you had 10 polling stations, you will have 10, you have to sample. So
you have 10 within steps of your Gibbs sampler.
For each polling station, you will have a step like that. But they are independent.
Right.
Okay, so the fact that you have several polling stations does not make the problem more difficult, actually. I mean, it's more expensive, but
so
they are conditionally independent.
It's obviously harder to scale, but then
yes, exactly. That's a good point.
The question of whether the polling stations are independent is questionable, right? Because ultimately, all the voters are exposed to the same information.
But the fact that they have some commonality is encoded in the model, I think.
Right.
But it's something you could discuss, yes. Yeah. Right, so the kind of MCMC sampler we're going to develop, I should stop moving to the screen because people online are not seeing me when I do that. Sorry for that, guys. We are going to design a MCMC sampler that leaves invariant the posterior distribution of theta given the data, which is y, okay? So the posterior is like the prior times this quantity, which again is the probability you observe x equal y, okay, given for a fixed parameter theta. So the question is again, how do I compute this? Which is just this quantity again before, this probability, okay? We're going to design a MCMC sampler where we replace this quantity by an unbiased estimate. So here I'm just describing a metropolis sampler. You propose a certain value according to kernel Q. You accept reject according to a certain probability, right? This is the acceptance probability. Here, this is not possible to do that because, again, you cannot compute this quantity. But it's possible to replace it by an unbiased estimate. And you would get, in the end, MCMC kernel that still leaves invariant the true posterior distribution. It's a bit magical, but some people might have heard about it. It's called the pseudo-marginal MCMC that has been developed before, right? So as soon as you know that you have this possibility of doing exact MCMC, as soon as you can derive an unbiased estimate, whole jump becomes, how do you derive an unbiased estimator of this probability, okay, which is the probability that AX equal Y, right? Right, so that's where we go into uncharted territory. at least for people doing MCMC, because kind of tricks that are not so difficult, maybe not so novel for another area of applied mathematics, but I'm pretty sure nobody tried anything like this before. What I'm doing works if you're able to compute exactly the characteristic function of X, right? So again, X is my flattened matrix. It could have a multinomial distribution, for instance, but I need to be able to compute the characteristic function, which is this expectation of exponential of itx, okay? You know, this kind of quantity you're introduced to when you do probability, and you never think about it again, because we're going to play with that one. So first remark, what is very convenient with the characteristic function is that if you give me the characteristic function of x, it's easy to get the characteristic function of ax, right? Because it's just a linear transformation, and the characteristic function of ax is just the characteristic function of x applied to A transpose Z, right? If you just write it down here, if I replace x here by ax, you can see you can get phi x evaluated at A transpose Z. Is that clear to everyone? So if you have a characteristic function of x, you can get the characteristic function of ax. Second thing to know about characteristic function is that it's a Fourier transform of the density or the probability because x is discrete. And then you can apply the Fourier inverse formula. So you can get your probability as the inverse Fourier transform of the characteristic function. Okay? So here I have a I have a formula for this probability, which I want to compute, is expressed as this integral. And here this function is a closed form. I can compute it. Right? So it already gives you a solution to the problem. Again, the problem was, can I derive an unbiased estimate of this probability? Here I recognize some integral. So I do a naive Monte Carlo. I'm going to sample uniformly from between minus pi and pi power dy, which is easy to do. I'm going to compute this kind of averages. Okay? Just a basic Monte Carlo. Little thinking went into this. We are going to do better than this, but it's a first solution. Yes? Can
you give us maybe an idea of like what dy is, like in terms of like order of magnitude?
Right. So in our application, the matrix X is like, so wait, the matrix X is like 15 by 4 or 15 by 3, so 60. And because you compute the row sum and row columns, dy is going to be less than 20.
Okay.
Yeah. But it's just this application. More generally, what you have to think is X is like a big matrix, like d by d, so d squared, and Y might be of order 2 of d, because you're computing only the sums. Right, so that's where we try to be a bit smarter than what we did. So again, I'm back to this formula. The probability I want to compute is equal to this integral, right? It's a funny integral because it's the integrand is a complex number, but forget about that, it's detail. Because we're computing in our application sums of the rows and columns, you might expect that AX behaves more or less like a Gaussian, okay? Typical in statistics, you have thousands of people having certain behavior, and you average, if you sum of rows and columns, it should be Gaussian-like. All right, so let's assume that AX has a closed Gaussian distribution, which would be something like that, okay? It's assuming I can actually compute the expectation on variance of X, then an approximation of the distribution of AX is this Gaussian. That's funny, but the characteristic function of a Gaussian with a covariance matrix sigma has a form expression. You can check on Wikipedia, and you get a Gaussian PDF, but with the inverted matrix, right? So if your variable has a variance sigma, then the characteristic function is with variance inverse of sigma. That means what? That means that in this integral, this phi x of z, so for the people in line, let me see. This guy, it should be close to a Gaussian, but again with this inverted matrix fix. So when you realize that, if you're a little bit in the business of Monte Carlo, you can think of important sampling. Important sampling is just this strategy where you write an integral with respect to some base measure or base distribution so that the integrand is as constant as possible. So we're going to do important sampling, and the proposal will be this one. Okay, notice the inverse is just because this is a characteristic function. So it's also a Gaussian density, but you have to invert the covariance matrix. Okay. So at this stage, again, I'm not sure how familiar you all with the Monte Carlo, but it's just one of the basic things you could try. Ask me if it's unclear. Right, so that's the smart part occurs here. So again, remember that the type of model we consider for X is like a multinomial distribution, like a very basic parameter family of distribution, which also is exponential. And when you play with exponential families, one thing you can do is tilting. What is tilting is this. So here you have your distribution or probability if X is discrete. I'm multiplying this distribution or density or probability with exponential rho Tx, and then I divide by some quantity so that you're back to something that sums to 1, so that it's again a probability. So you can see it's just a change of measure. It's a parametric change of measure. Each row gives you a tilted distribution. With this, you tilt the distribution towards the left or the right, given the value of rho in a certain sense. You can check this mx, this normalizing constant, is actually the moment generating function of x because it's the expectation of this quantity under fx. Okay, so that's tilting. Why tilting is interesting in your situation? So recall that x was multinomial. If you try to tilt a multinomial distribution, you get another multinomial distribution, but with a different parameter. So here imagine P is a vector of probabilities, it's sum to 1. Then the new tilted distribution will have tilted probabilities which are proportional, which is like P times exponential of rho of J. Okay, so for each J, the two are proportional. And then on the left, to get the actual new probabilities, you normalize so that the sum is 1. Right, so what I'm saying here is if you consider a multinomial model, if you do tilting, you're still in the same family of multinomial distribution. Okay, you can say that's nice, but what's the point of this compared to the rest of the talks? So this property is more general. I mean, you can use it as soon as you have an exponential family. Right, so in our case, who cares? We're trying to compute the probability of AX equal Y, okay? But the funny thing is that when you tilt the distribution of X, it defines a tilting on AX. Again, it's because of the linearity. So that's how you derive what I've just said. You can check quickly. This is the density of AX rho. So that means I'm trying to compute the density or probability of AX, but when X has been tilted, okay? And you compute it like that. And in the end, if you, for this parameter rho, the tilting parameter rho, if you assume that it's of the form A transpose nu, then you can check, in the end, you get for the density of X row, you have the same structure, right? So what I'm just saying is that the way you tilt the distribution of X translates into a way you tilt the distribution of AX, right?
So what you're effectively saying is that tilting X is the same as tilting AX, but then you have a one-to-one correspondence between the tilting parameter or coefficient.
Not one-to-one because of this, you see? So maybe I should, sorry guys, just 1 minute, I will repeat after. Look at the calculation. So this is the probability you get Y. You make the sum of all possible X's with the indicator function. And here I just plug the expression from the previous slide. Okay? And here you want to put this outside. And so, but it depends on X. So if you assume rho to be A transpose mu, then rho Tx equal this. It doesn't depend on X anymore. It gets out, and then you get this expression.
So that's the trick. Then you need to assume a specific form for rho.
Yeah, it doesn't work for all the rho because you said one-to-one. Rho makes it possible to, I mean, you have less freedom for tilting AX than for X. I mean, with any rho, you can tilt the distribution of X, but you have to assume that rho equals this to obtain a tilting for AX. So the dimension of the tilting is lower, which kind of makes sense because the dimension of, if you see it's rho Tx, so the dimension of the parameter has to be the same as the observation, right?
Yeah.
Right. I hope it was clear for people online, but I think you can also interrupt me, hopefully, if he has any question. Right. So to conclude, if you define a tilting on X, it leads to a tilting on AX. Again, at this stage, you could be lost and say, yeah, okay, but what's the point of all this? Why do we care? It's just mathematics, it's just some calculation of probabilities. Right, so look at this expression. So for people online, I'm talking about this one. Equation 6, okay? This says that given the probability you want, you can define another probability. But the one on left, you don't care about it. You still care about that one, okay? So you care about the one on the right-hand side. So what I'm going to say, if I'm going to flip the relation, and I'm going, if you forget the hats for the moment, I'm just going to say, oh, the probability I want to compute can be re-expressed like this. I know when I put a hat in statistics, it means I replace a quantity by an estimate. So this is just a way of saying I have an extra liberty if I want to estimate my probability of changing the base distribution using a certain tilting, right? So I had already a strategy for estimating this kind of probability, but maybe if I consider a tilted distribution, I could end up with a lower variance, okay? So that's what I'm doing here. The question then, of course, is how do you choose this new, okay? So I'm just, again, in the context of using importance sampling, you could just say, oh, it's a bit like changing the proposal distribution. But it's a bit more subtle because here I'm changing the quantity I want to estimate because, again, between these two quantities, this one and this one, there is this simple relation. Okay, so this part is just something you can compute exactly, and here I'm just using this. So then we have in the paper some way of choosing new that minimize the variance. So I kept this equation 8 to please Theo because he's convinced that this equation, the solution, minimize the variance. I'm pretty sure it's not true, but it's a good solution to the problem. Please have a look at the paper if you want to understand the rationale behind it, but we don't have this, it's a heuristic for the moment. The result we have, which I like. We can show that when you do this tilting, you can have a variance of for your estimate that goes to 0. But wait, when I say goes to 0, it says n goes to infinity, where n is the data sample size. Okay, I'm not talking about the Monte Carlo sample size. When the Monte Carlo sample size goes to infinity, the variance should go to 0. Hopefully it's true. No, here what happens is that when n goes to infinity, this heuristic approximation I mentioned before, that it's more and more Gaussian, is more and more true. And if you do the tilting, you can check that doing the tilting is like changing the distribution so that you're in the center of the distribution. And if you do the tilting, you have this. If you don't have it. So it looks what you're doing, it does not, it's not stupid. At least asymptotically, it's kind of optimal, right? Yes?
Sorry, what's n in the voting case? Is it like the polling stations? Or?
N is the number of people who go voting. It's the number of people in the polling station, essentially. Like, let me show you. Here, you see, if I have only one polling station, this matrix X will be a multinomial. I should put that actually. It's like a multinomial distribution, but multinomial distribution, there's also parameter n, which is the number of people who vote. Yeah, so that's this n that goes to infinity. Okay, and that's missing from this slide. Actually, I should put n. My bad. Okay.
Sorry,
yes.
If you go back to the slide, I think, sorry, the one before where you define, so question 7.
Mm.
So in there, effectively, mu is left as a parameter, so it's a free parameter.
It's a free parameter.
What about mx? How costly is it to compute mx?
You have a closed form formula for the
closed form. Okay.
For the multinomial distribution. If I remember correctly, it's a closed form, yes.
Right. Yeah. Because that, I mean, the result you have in the following slide is insanely powerful, right? I mean, the asymptotics doesn't actually depend on how many iterations you have. It only depends on the entire data set. Yeah.
What's going on is that when the more people you have in the polling station, the more if you think of a multinomial distribution, it's quite clear that when n is large, yeah, if you divide by n, it behaves like a Gaussian. Okay.
Right.
But when you compute the probability you're equal to y, maybe this y is in the tails of the distribution. Yeah. So what the tilting does, moves the Gaussian so that you're exactly in the center.
So you're skewing the distribution. Yeah. That's what's happening.
Yeah, yeah. I should find a better way of explaining this in the slide.
I mean, in layman's term, that would be equivalent to saying, even if I have a very shitty predictor for one particular polling station, there are just so many voters that eventually I'll get it right. Does that make sense?
Yeah.
It's not very popular with polling companies.
The way to think about it is that, oh, I have this polling station, they're weird. They're twice more likely to vote Macron, say. So the probability of this happening is small, but let's assume that I change suddenly the distribution of the probability you vote Macron is higher, and then I can compute more easily the probability that they voted for this.
Does it then make sense to consider polling stations are particles, as in particle filtering problems, and then you're effectively weighting some of those particles depending on the performance, and the performance to be understood in the sense that if you're close to the unskewed latent distribution, then you're good, otherwise you're bad. Does that even make sense?
I'm not sure, because when we do this tilting, it's not like we are assigning a weight to the polling station there. In the end, in the model, they still have the same importance. We just do this tilting to reduce the variance of the unbiased estimate. Right. So there's no notion of reweighting the polling station. Where we're doing this, it's not really a reweighting scheme. It's just we're changing the base measure. I think so. Yeah. Okay, so to give you an idea in our kind of application, when we started with a uniform estimator, you needed like 100 million points for a given, that should be YK. We're gentlemen, my co-authors and I, but we strongly disagree on notation, so in the end, give slides. But anyway, well, Robin and I agree, actually. Still, anyway, it should be YK. And if we do the Gaussian proposal on tilting, for having the same level of error, 10 points are enough. So you see it's quite strong impact. And you can see that's a numerical experiment where you have simulated data from the model. So it's like an artificial polling station, if you want. And on the x-axis, you have a number of people who vote. And this is the standard error of your estimator. And you can see that if you do a Gaussian proposal plus tilting, then indeed the variance is already small at the beginning, but it gets better and better. That's a relative variance. It's like a variance divided by a square of a true quantity, right? Like you're estimating a probability. So, no, it's like standard deviation divided by the probability. So it's a relative error. Okay. So it works better, and the way it works better is improve as you increase n. And fortunately for us in our application, you have a mini polling station of order of size 1,000. Right. So if you're happy with this, it's time to talk about politics, Benjamin. 2007. 2007 was an election where you had, so if these names mean nothing to you, Sarkozy is was right-wing candidate. No, he's in jail or close to it. No? Royal was the socialist candidate. Bayrou is the interesting one from a political science point of view, because Bayrou comes from the center-right party, and I think it was the first election that, so he didn't make it to the second round, and he made history by saying he would not choose between Sarkozy and Royal. Whereas before, if his party would always align to the right. Do you agree on this?
I do agree, and interestingly, for those of you who are not fortunate enough to be close to French politics, he's the current prime minister.
He's the current prime minister, yes.
So he ended up prime minister of Macron. So anyways. Le
Pen is far right, abstention is you don't vote. Others, there are many other candidates, even crazy one who believes in a UFO and stuff like that. But you know what I'm talking about?
Yeah, I do. So hang on. So all of those rows should be one, right? Abstention doesn't sum up to one.
What is?
Or maybe it's just a rounding error. Okay.
I forgot what this. Okay, so here for this election, we assume this the simplest model. That is, this probability Pij are constant across polling station, which is a very simplistic model. And here I'm estimating these probabilities. So you can see the sum here is 1, and this is 1. You're saying here the sum is not 1?
No, the sum up for abstention, but never mind. Probably it's fine.
Last two rows.
Yeah.
Okay, I need to check that with my co-authors. Anyway, this is unsurprising. If you vote for Sarkozy first round, it's very likely you vote for him second round. Same thing for Royal. And then for Bayrou, you can see almost equal split between Sarkozy and Royal, but still it's people who are more likely to go right-wing. Okay. And this is also interesting because, but we're going to talk about that again. When people vote for far right or far left, you don't know whether in the second round they will get closer to the center, or they would abstain, or they would do other things. So here, in 2017, still 70 people who voted far right moved to the right on the second round. But there's still a lot of abstention among these voters. A posteriori, it sounds like pretty reasonable, but this is the kind of stuff that people debate on TV, and they make a wide assumption. The data tells you things quite clearly, and I'm just reporting like the posterior average, but the posterior variance is super small actually. That was interesting. Okay, so there are a lot of young people in the audience, so let's move to a more recent election, 2022. So there are the three main candidates, or the three people who were the top three in the first round. So this is far left, Mélenchon, Macron, center right, and Marine Le Pen, far right. And the two people who made it to the second round is Macron and Le Pen. So then the question is, people who voted Mélenchon first round, did they move to Macron or to Le Pen or to abstention, right? And again, this is something that people really would like to know, because first hypothesis, you always vote for, even if your candidate who is far left did not make it, you move to the one which closest to you, because you are more afraid of the one on that more extreme. Or alternatively, there are people who say, in French, the extremes is like on a circle, right? There are this hypothesis. You will always vote for fringe candidates.
So your first assumption is effectively assuming the political spectrum is metric.
Yeah.
Which is debatable.
But, right, so we have like 60,000 polling station. Again, I think it's the first time people managed to study this data without any kind of aggregation. So that's pretty nice. We are counting for 49 million people who vote. So it's a very big, in terms of ecological invariance, the data is pretty big. Theo played with JAX on GPUs, and for this it took 4 or 5 minutes, etc., etc. And statistically speaking, I'm talking about estimates, but you can also compute base factors and to compare models actually.
So, Nicolas, training here refers to what? To computing the equation 7 you had used.
It's just to sample from the posterior.
Okay.
Yeah,
and that's reporting the average.
Yeah. Right, so that's super. That's the best plot. That's the one Benjamin should appreciate the most. Third model, which is a bit smarter, we make the probability you vote for Le Pen second round, given that you voted Mélenchon first round, a function of population density. Okay. So the question is whether this transfer from far left to far right or far left to center depends on the population density. It does. And so on the left, you have more rural areas with a low density. On the right, the top right, you have Paris, essentially, or big cities. And you could see that this transfer from far left to far right, it does exist, but it's already quite small in low density regions. And then it decreases with the density. Right, so this hypothesis 2 seems to be rejected, and people tend to move to the center. If they were voting far left, they would move to the center, and it's even more likely that they do so if you live in big cities. Yes.
So 2 quick questions. What about abstention? Because the third assumption is that obviously you voted for Mélenchon in the first round and then you abstain because you're not happy with the 2 candidates which are left. And the other one is, what about your assumption that all polling stations were independent? You're violating this by focusing on the population density.
Right. So first question, so everybody is voting Mélenchon, and that's Mélenchon to Le Pen, Mélenchon to Macron, Mélenchon to anything else. So it could be abstention, but could be also invalid.
Yeah, okay.
You see what I mean? Yeah. Vote blanc. So you account for 3 possibilities. So your second question, so we are using this third model where you explicitly assume that these probabilities, they are different in the different polling stations, and they are a function of density. We have some model that use, it's just a logistic. You just a logistic with extra parameters, and we estimate the parameters. So I found this very interesting because before I did this study, personally, I had no strong opinion. It looks like people who claiming that people who move easily from far left to far right, they're wrong. It's much less common than you would think. And if it happens, it's more common in rural areas than in urban areas. So I don't know what you think, Benjamin. I find it interesting.
I mean, in the end, what your plots are showing is that a majority of people actually abstain. Because of probability mass.
Yes. Yes. Yeah, I was talking mostly about this one.
Yeah.
You're right. Yeah. People are more likely able to abstain or to move to the center, but there are very little probability they move from far left to far right.
And there might be also a, let's say, some kind of a survivor bias, because for very low densely populated areas like the countryside, actually Mélenchon did very low scores, right? So the actual number of voters in those small areas is very low. So the proportion being low of moves, to the far right is significant, obviously, but you're talking about very small samples, if that makes sense. I mean, yeah, that's more of a political question than a statistical question.
It's a good point. Again, we are using all the data here, so there's still some. I mean, you can see that these are confidence intervals, so we are still quite.
I mean, you should go to French TV with that plot.
Yeah. Let's go to the pub, and I'm a bit worried actually, but French journalists, they are really stupid. Really stupid. All right, so let's move even closer. So Emmanuel Macron at this decided to have a snap election to try to change the parliament. It didn't go well for him. That makes this time it's like we have many elections, because I'm talking about legislative election, and each circonscription, each constituency, you have different candidates. People who want to become MPs, and these people might be closer or not to more or less aligned to their party policies, whatever. So it's like you have many different elections with many different configuration. But there are many constituencies where you will have, again, these three major blocks: far right, center, far left. And then in the second round, you can have between 2 and 4 candidates. Is at most 4, or it could
be? At most 4, because you need to have 12.5% of people registered to vote, other people actually voting.
Okay, and so multiply by 4. Yeah. So in presidential election is the top 2 who go to the second round. In legislative election, it could be top 2, top 3, top 4 based on their results. And then in the second round, when you have 3 candidates, there are strategies like people who really dislike the far right. Are we recorded? I mean, in a few years, I will have problem with this. Anyway, okay. So the notion of Front Républicain that was discussed a lot on French media was this notion that people are being strategic and trying to do whatever they can to avoid having a far-right candidate winning, right? So that means that if you voted for one of the 3, but it's the weakest of the 3, you might decide to discard your vote or to vote for one of the top 2. And the candidate himself or herself could decide to step back just to increase the chance or decrease the chance of a far right. Okay, so to summarize this, on the left, the weakest of the 3 decided to leave. Right, so in the top left corner, the weakest one was the far left. And this is the histogram represents the variation in the different polling stations. It represents the probability that a voter from the far left decided indeed to vote for the center candidate, right? And you can see in many polling stations, people decided to move to the center. This is where, again, the weakest lives, but the weakest was the guy in the center. And you can see that people who vote center were less likely to vote for far left or left at the second round, right? And this is the case where you have 3 candidates, but they decided to stay because they are being petty, essentially, and I still want to try to win. And then you can see voters tend to stick with their candidates when the candidates don't leave. Right? So a very small probability you switch, but some people do. And again, there's no big difference between these 2 configurations. So again, this one is the weakest was far left, and this one is the weakest was the center. When I say left, far left, it's a bit debatable because because there was people who could be. It depends what you define to be left and far left, and the different parties in this left/far left coalition. That's even the more fancy model. You try to study these probabilities as a function of a score of the far right. Okay, so the idea was if the score of the far right is higher, is it more likely that you switch to make sure that the far right doesn't win? And you think that it seems to have an opposite effect. That people they see no hope, so they don't try to switch. But as you can see, the slope is not very significant. There's a lot of noise. So again, each dot is a polling station here. And if I represent this dot, I'm completely ignoring the posterior variance for each polling station, but typically they are very small. Okay, this is the point here of these slides is to show you all the kind of crazy stuff you can do with this kind of data and with this kind of methodology, which is kind of super interesting in your if you're in political sociology. Right, so this is just one application. We did it very thoroughly, and I should have said maybe initially that Theo was our intern, but he graduated from Sciences Po, which is a Parisian school in politics, so he knows a lot. He helped us a lot to look at the right problem, right constituency, etc. We are also a bit excited, quite excited actually, about other potential application. So whenever you have aggregated data, right? You have so for instance in France, INSEE is the Institute of Official Statistics, and they report a lot of aggregates at a local level. Like this neighborhood in London, the average salary is this, but you're not going to give or maybe you're going to provide quantiles, but not more than that because you want to protect the privacy of people living in this neighborhood of London. Okay. So aggregation is a very simple way to achieve privacy for public data. But with this kind of approach, maybe you can develop models for individuals and still unfair parameters. Network tomography is another one I find quite exciting. So a network is a discrete structure. And it's very common, you don't observe exactly the network, but you just observe, for instance, the average speed when a message goes through the network. Okay. Latin square is a funny one. You can think of Latin square as, if you want to count the number of Latin squares, it's a bit a problem where you have a matrix X and you impose constraint on the sums on the rows, etc. This is the paper, it's on archive. It has been submitted a few months ago. And if you have any question, feel free to ask.
Thank you, Nicolas.